Picture this. You're standing at the starting line of a drag strip in the early 1970s, and the air smells like burnt rubber and high-octane fuel, and you hear something you've never heard before. It's not the deep rumble of a typical big block. It's a scream, a banshee wail that cuts through every other sound at the track, and it's coming from what looks like a regular Pontiac GTO. But when the hood comes up, your jaw drops, because sitting on top of that engine is a towering aluminum intake manifold, crowned with not one, but two massive four-barrel carburetors, reaching toward the sky like some kind of mechanical cathedral. And the guy behind the wheel? He's not a factory-backed driver. He's not some corporate engineer with a PhD. He's a farmer from Georgia, and he's about to embarrass one of the biggest automakers on the planet. This is legacy motoring, and I spend way too much time thinking about the engineers and backyard builders who proved the factories wrong. If you're someone who loves the untold stories of drag racing legends and the genius engineering behind the most powerful naturally aspirated engines ever built, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, let me take you back. Let me take you back to a time when the American automotive industry was at war with itself. We're talking about the late 1960s and early 1970s, the absolute peak of the muscle car era, and every manufacturer was trying to outdo the other. Ford had the Boss 429, Chrysler had the Hemi, Chevrolet had the LS6 454, and Pontiac, well, Pontiac had just released what they believed was the ultimate expression of big block power, the 455 cubic inch V8. This wasn't just another engine. This was the largest displacement engine Pontiac had ever produced. The bore measured 4.15 inches. The stroke stretched to 4.21 inches. You do the math and you get 455 cubic inches of pure American displacement. And the engineers at Pontiac, led by the legendary John DeLorean and his team, believed they had created something that didn't need any help from the aftermarket. They were absolutely convinced that their single four-barrel carburetor setup was the pinnacle of induction technology for this engine. Here's the thing. They weren't entirely wrong from a street car perspective. The standard 455HO came equipped with a Rochester Quadrajet four-barrel carburetor sitting on a cast-iron intake manifold, and it produced 335 horsepower at 4,800 RPM, with a stump-pulling 480 pound-feet of torque at just 3,600 RPM. For a street car, this was magnificent. You could roll up to a stoplight, barely touch the throttle, and the car would surge forward with the kind of effortless authority that made everything else on the road feel inadequate. The torque curve was like a flat mesa stretching across the entire usable RPM range. Pontiac's engineers had optimized every aspect of this engine for low-end grunt and mid-range punch. The intake ports were designed to create high-velocity airflow at moderate RPM. The combustion chambers promoted efficient burn at street-friendly compression ratios. The camshaft profiles were mild enough to pass emissions testing, while still providing that unmistakable muscle car idle. It was, by any objective measure, a masterfully engineered street engine. But here's what most people don't realize. While Pontiac was patting themselves on the back for their single carburetor philosophy, something very different was happening across the competitive landscape. Over at Chrysler, engineers had been developing tunnel ram intake manifolds since the early 1960s. Their max wedge program had proven that long intake runners, topped with dual four-barrel carburetors, could produce dramatic power gains in racing applications. The science behind it was elegant in its simplicity. Those tall runners created columns of air that would resonate at specific frequencies. When tuned correctly, the pressure waves bouncing back and forth inside those runners would arrive at the intake valve at precisely the right moment, literally ramming extra air-fuel mixture into the combustion chamber. It was like getting supercharger boost without a supercharger. No belts, no pulleys, no parasitic drag, just physics doing its thing. Chevrolet was in on it too. Their cross-ram intake setups on the Z28 Camaros were absolutely dominating the Trans Am racing series. Ford had their tunnel port 427s that were terrorizing NASCAR. Every major manufacturer seemed to understand the potential of resonance-tuned intake systems. Every manufacturer except Pontiac. Their official position, documented in internal engineering memos that have since surfaced, was crystal clear. The 455 does not require and will not benefit from dual-carburetor induction systems. The port geometry and combustion chamber design are optimized for single four-barrel operation. End of discussion. Now, you might be thinking, well, maybe they were right. Maybe the Pontiac 455 really was different from those other engines. Maybe there was something about its architecture that genuinely made tunnel rams ineffective. And honestly, there were some legitimate engineering arguments to support that position. The Pontiac V8 family had unique port angles compared to Chevrolet or Chrysler engines. The intake ports enter the combustion chamber at a steeper angle. The port cross-sections were different. The valve spacing was tighter. All of these factors meant that you couldn't just bolt on a Chevy tunnel ram and expect it to work. You need something specifically designed for the Pontiac architecture. And in 1970, nobody was really investing in that development. Nobody except one man. Enter Arlen Besswick, known throughout the southeastern drag racing circuit as the Farmer. And that nickname wasn't just colorful marketing. Beswick actually was a farmer. He ran a working farm outside Roswell, Georgia, and between planting seasons and harvest times, he raced Pontiacs. But calling him just a farmer would be like calling Leonardo da Vinci just a painter. Beswick had been racing since the mid-1950s, starting with a 1957 Chevrolet that he personally modified and campaigned to multiple class championships. By the time he switched to Pontiacs in the mid-1960s, he had accumulated more practical knowledge about high-performance engine building than most factory engineers would ever possess. He understood combustion dynamics not from textbooks but from thousands of quarter-mile passes, from reading spark plugs under fluorescent lights at 2 in the morning, from the feel of an engine through the seat of his pants. His speed shop in Roswell had become a pilgrimage site for serious Pontiac racers throughout the Southeast. If you wanted your 455 to make real power, you went to see the Farmer. And what set Beswick apart from the countless other speed shop operators scattered across the country was his absolute refusal to accept conventional wisdom without testing it himself. When Pontiac said their engines didn't need tunnel rams, Beswick didn't argue. He didn't write angry letters to the engineering department. He simply went into his shop, closed the door, and started experimenting. The tunnel ram manifold he selected was an aftermarket piece, likely an early Edelbrock or Weyand casting that had been designed primarily for Pontiac applications, but had seen very limited use. The manifold featured intake runners that stretched nearly 14 inches from the carburetor mounting pads down to the cylinder head ports. This runner length was critical because it determined the RPM at which resonance tuning would occur. The physics are straightforward. Longer runners produce resonance at lower RPM. Shorter runners produce resonance at higher RPM. The ideal length depends on the engine's intended operating range, the valve timing events, and the desired power band characteristics. Beswick understood this intuitively, even if he might not have been able to write the differential equations that describe acoustic wave propagation in taper tubes. On top of that towering intake manifold, Beswick mounted two Holley 750 CFM 4-barrel carburetors. Let that number sink in for a moment. Each carburetor was capable of flowing 750 cubic feet of air per minute at wide open throttle. Together, they provided a theoretical maximum flow of 1,500 CFM. To put that in perspective, the factory Rochester Quadrajet on the standard 455HO was rated at approximately 750 to 800 CFM. Beswick had essentially doubled the breathing capacity of the induction system. But here's where it gets really interesting. Raw airflow numbers are meaningless without proper fuel metering. And this is where the vast majority of people who tried to replicate Beswick's setup failed miserably. Look, bolting two carburetors onto a tunnel ram is the easy part. Any competent mechanic with a set of wrenches can do that in an afternoon. The hard part, the part that separates engineering from part swapping, is making those two carburetors work together in perfect harmony across the entire operating range of the engine. Each Holley 4-barrel has primary and secondary throttle plates, accelerator pumps, power valves, idle circuits, main metering circuits, and transition slots. When you have two of them sitting side by side on a common plenum, Every single one of those systems has to be synchronized with its counterpart on the other carburetor. The primary throttle plates have to open at exactly the same rate. The secondaries have to transition at exactly the same moment. The float levels have to be identical to within a 32nd of an inch. Even the fuel pressure delivered to each carburetor has to be equalized, because any difference will cause one bank of cylinders to run richer or leaner than the other. Beswick spent weeks, and by some accounts months, perfecting the carburetor calibration. He'd make a dyno pull, shut the engine down, pull all 8 spark plugs, and examine each one under a magnifying glass. The ideal condition was a light tan insulator with a faint ring of color change at the tip. Too white meant too lean, a condition that could melt pistons and burn valves. Too dark meant too rich, which cost power and fouled plugs. But it wasn't just about getting all 8 plugs to look the same. Each cylinder had its own personality because of variations in port flow, runner length, and combustion chamber volume. Beswick had to find the jetting compromise that kept every cylinder within a safe operating window while maximizing overall power output. The front carburetor, the one closest to the firewall, consistently needed different jetting than the rear carburetor. This wasn't a defect in the manifold design, it was simple physics. Air entering the rear carburetor had a straight shot into the plenum, while air entering the front carburetor had to make a slight directional change. This created subtle differences in air velocity and distribution that required compensating fuel calibration. Beswick eventually settled on primary jets that were 2 sizes richer in the front carburetor than the rear, with secondary jets 1 size leaner. The accelerator pump cams were different too, with the front carb running a more aggressive pump profile to prevent a lean stumble during hard throttle transitions. But the carburation was only one piece of the puzzle. The real magic, the component that transformed this engine from a mildly interesting experiment into a quarter-mile weapon, was the camshaft. Pontiac's factory camshaft offerings for the 455 were conservative by any racing standard. Even the most aggressive production cam, the number 068 hydraulic grind, had modest duration numbers and was essentially finished making power by 5,500 RPM. This was perfectly appropriate for a street engine, but it was completely wrong for a tunnel ram application. Those long intake runners needed time to fill. The resonance effect that made tunnel rams work required the valve to stay open longer than a street cam would allow. The air column bouncing back and forth in those 14-inch runners needed a specific window of valve open time to deliver its charge effectively. Beswick commissioned a custom solid lifter camshaft from one of the era's top cam grinders, likely either Crane or Iskandarian. The specifications were aggressive by any standard and absolutely radical by Pontiac standards. Intake duration stretched to approximately 320 degrees at 50 thousandths lift. Exhaust duration went even further to 328 degrees. Valve lift, with Beswick's chosen 1.65:1 ratio rocker arms, soared to 0.580 inches on both intake and exhaust. The lobe separation angle was tightened to 106 degrees, which increased the valve overlap dramatically. This overlap period, when both intake and exhaust valves are open simultaneously, is critical in high-performance applications because it allows the outgoing exhaust pulse to help pull fresh intake charge into the cylinder through a scavenging effect. Now, you might be thinking, those cam specs don't sound that extreme by modern standards, and you'd be right. Today's pro-stock engines run far more aggressive profiles. But you have to remember the context. This was 1971. Flat tappet camshaft technology imposed severe limitations on lifter acceleration rates. You couldn't just grind any profile you wanted because the flat lifter face had to maintain contact with the cam lobe at all times. Too aggressive a ramp rate and the lifter would separate from the lobe, a condition called lofting that caused catastrophic valve train failure. Beswick's cam was pushing the absolute limit of what flat tappet technology could survive. The consequences of this cam choice were dramatic. At idle, the engine sounded like it was dying. It loped and bucked and stumbled at anything below 1,200 RPM. The vacuum gauge at idle read so low that power brake boosters were useless. The engine would barely pull itself off the starting line at low RPM. Below 3,000 RPM, it was genuinely slower than a stock 455. Customers who came to Beswick's shop and heard the engine idle for the first time often thought something was wrong with it. It sounded broken. It sounded sick. It sounded like a terrible mistake. But something extraordinary happened when the tachometer needle swept past 4,500 RPM. The engine didn't just wake up. It transformed. It was like flipping a switch connected to a different universe. Those long intake runners began to resonate. The air column started pulsing in synchronization with the valve events. The pressure waves reflected off the carburetor throttle plates and arrived back at the intake ports at precisely the right moment, ramming extra charge into the cylinders with an authority that defied natural aspiration. The dyno needle, which had been climbing lazily through the lower RPM ranges, suddenly shot upward with a violence that startled even Beswick the first time he saw it. Let me walk you through the physics of what was actually happening inside that engine at peak power. As each intake valve opens, it created a negative pressure pulse that propagated up through the intake runner at the speed of sound, roughly 1,100 feet per second in the hot air-fuel mixture inside the runner. When that pulse reached the open end of the runner at the carburetor throat, it reflected as a positive pressure wave and traveled back down toward the valve. The time for this round trip was determined by the runner length and the speed of sound. With Beswick's 14-inch runners, the round-trip time corresponded almost perfectly to the valve open duration at 6,800 RPM. At that engine speed, the reflected positive pressure wave arrived at the intake port just as the valve was beginning to close, literally stuffing extra mixture into the cylinder against a rising piston. The effect was equivalent to approximately 3 to 4 pounds of boost from a supercharger, achieved entirely through acoustic tuning. The dyno results were staggering. Beswick's tunnel ram 455 produced approximately 650 horsepower at 6,800 RPM. To appreciate how remarkable that number was, consider the context. The factory 455HO, Pontiac's hottest production engine, made 335 horsepower. Beswick had nearly doubled the output. In terms of specific power, his engine was producing 1.43 horsepower per cubic inch. The best NASCAR Cup engines of the era, built by factory teams with enormous budgets and dedicated engineering staffs, were making approximately 1.3 to 1.5 horsepower per cubic inch. A farmer from Georgia was matching the output of the most sophisticated racing engines in America using an engine that Detroit said couldn't benefit from tunnel ram technology. The torque characteristics were equally impressive, though fundamentally different from the factory engine. Where the stock 455 produced its peak torque at a lazy 3,600 RPM and tapered off quickly above 5,000, Beswick's engine didn't even start making serious torque until 4,500 RPM. But from that point upward, it maintained over 500 pound-feet of torque all the way to 6,500 RPM, with peak torque of approximately 540 pound-feet occurring at 5,800 RPM. This broad, flat torque curve was the key to its quarter-mile performance. The engine pulled relentlessly through the entire run, never falling off, never losing momentum. In superstock trim, with the car ballasted to meet class weight requirements, Beswick's tunnel ram GTO was turning quarter-mile times in the low 10-second range at approximately 134 miles per hour through the speed traps. The factory single carburetor cars in the same class were running a full second slower, which in drag racing is an eternity. A full second at the top end of superstock competition meant the race was decided before the cars reached half track. Beswick wasn't just winning, he was making the competition look like they were running a completely different class. Now, here's where Beswick got really clever, and this is something that separates the true competitors from the guys who just show up with fast cars. He understood that drag racing isn't just about horsepower, it's about strategy, psychology, and knowing how to manage information. During warm-ups and qualifying sessions, Beswick would run his GTO with a conventional hood scoop that completely concealed the tunnel ramp setup beneath it. From the outside, the car looked like any other modified 455 Pontiac. Nothing special, nothing alarming. Just another big block GTO in a field of big block GTOs. Competitors would look at his qualifying times, which Beswick deliberately sandbagged, and think they had him figured out. They'd set their dial-ins and plan their strategies based on what they'd seen. Then elimination rounds would begin, and Beswick would remove the hood scoop. Those twin Holleys would suddenly be visible, reaching for the sky like chrome-plated skyscrapers, and you could literally watch the confidence drain from his opponents' faces. By the time they realized what they were up against, it was too late to adjust. They were locked into their qualifying performance. They were committed to a race strategy built on incomplete intelligence. And when the Christmas tree dropped and Beswick launched that tunnel ram monster, the sound alone was enough to break their concentration. Those twin carburetors sucking air through velocity stacks created a shriek that was unlike any other Pontiac on the circuit. It wasn't a rumble, it wasn't a growl, it was a scream, a mechanical banshee wail that announced in no uncertain terms that something very different was happening under that hood. The psychological warfare extended beyond the starting line. Word spread through the superstock community like wildfire. Racers would arrive at events and ask the same question before they even unloaded their cars. Is the farmer here? If the answer was yes, you could see the calculations happening behind their eyes. Some adjusted their strategies. Others, the smart ones, tried to avoid Beswick's side of the elimination bracket entirely. The less strategic ones convinced themselves that their cars were fast enough and lined up against him anyway. Most of them went home early. And here's the thing that really frustrated his competitors. They tried to copy him. Of course they did. Success in drag racing has always been followed by imitation. Other Pontiac racers would go out and buy tunnel ram manifolds. They'd bolt on a pair of Holleys. They'd fire the engine and expect magic. And what they got was a car that ran slower than it did with a single carburetor. They'd show up at the next race confused and angry, asking anyone who would listen why their tunnel ram didn't work. The answer was always the same, and it was always the answer they didn't want to hear. A tunnel ram isn't a bolt-on part. It's the centerpiece of a complete system, and every other component in that system has to be designed to work with it. The camshaft profile, the compression ratio, the cylinder head port work, the ignition timing curve, the exhaust system, the carburetor calibration, the valve spring pressure, the push rod length, the rocker arm geometry. Change any one of those variables without understanding how it affects the others, and you don't have a race engine, you have an expensive paperweight. The compression ratio in Beswick's engine had been carefully selected at 12.5:1, achieved through custom-forged pistons with precisely calculated dome volumes. This was about as high as you could safely run with the 104-octane racing fuel available in 1971. Higher compression would have produced more power, but it also would have pushed the engine into detonation territory, where uncontrolled combustion pressure spikes could crack ringlands, pound rod bearings, and eventually send the connecting rod through the side of the block. Beswick understood that the fastest engine isn't the most powerful one, it's the most powerful one that survives the entire elimination round. The cylinder heads received extensive modification. The intake ports were enlarged and reshaped to flow more air at high lift values, matching the aggressive cam profile's demands. The exhaust ports were opened up to prevent reversion and improve scavenging during the extended overlap period. Valve sizes grew to the maximum that Pontiac's combustion chamber architecture would accept, 2.11 inches on the intake and 1.77 inches on the exhaust. The combustion chambers themselves were carefully unshrouded around the valves to improve flow at high lift, and every chamber was CC'd and matched to ensure equal compression across all 8 cylinders. The bottom end was built to survive what Beswick knew the tunnel ram would demand, sustained operation at 7,500 RPM with violent shifts that sent momentary shock loads through every component. The factory cast connecting rods were replaced with forged steel pieces. ARP fasteners replaced factory bolts throughout the engine. The main bearing caps were align honed to ensure perfect crankshaft geometry. The oil system received a high-volume pump with a stiffer pressure relief spring to maintain adequate film thickness at the elevated RPMs. A deep sump oil pan with baffles and a windage tray prevented oil starvation during hard launches, when centrifugal force would try to push the oil away from the pickup tube. The valve train was another area where Beswick's attention to detail separated him from the imitators. Those massive valve springs had to control 0.580 inches of valve lift at 7,500 RPM without floating, bouncing, or braking. The spring pressures were enormous, over 400 pounds on the seat and nearly 700 pounds at full lift. These pressures imposed tremendous loads on the cam lobes and lifter faces, accelerating wear and requiring frequent inspection. Beswick would replace valve springs preventatively every 40 to 50 passes, never waiting for them to show signs of fatigue. A broken valve spring at 7,500 RPM meant a dropped valve, and a dropped valve in a 12.5-to-1 compression engine meant catastrophic and expensive damage. Let me also talk about what it was actually like to drive this thing, because I think that gets lost in all the technical discussion. First, starting the engine was an adventure in itself. The high compression ratio and radical camshaft meant the starter motor had to spin the engine fast enough to generate sufficient cylinder pressure for ignition. The battery had to be fully charged. The starter had to be in perfect condition. Even then, the engine would crank for several seconds before catching, and when it did fire, it sounded like it was running on 4 cylinders. The aggressive cam timing meant that at idle speed, the intake and exhaust valves were open simultaneously for such a long period that cylinder pressure would bleed off, causing a rough, irregular idle that shook the entire car. Driving the car to the staging lanes required patience and technique. The engine would stumble and buck at low RPM, threatening to stall at every opportunity. The clutch was a multi-disc centrifugal iron unit designed for one thing only: engaging as violently as possible to maximize the launch. There was no modulation, no feathering. It was either locked or unlocked. This meant stop-and-go driving in the staging lanes was a constant exercise in clutch management, and more than one crew member had to push the car the last few feet to the water box because Beswick didn't want to risk overheating the clutch before the run. But once staged, once the pre-stage and stage lights illuminated, once Beswick brought the engine to its launch RPM of 4,800 RPM and held it there against the trans brake or line lock, the car transformed from an unruly beast into a precision instrument. When the last amber light on the Christmas tree flashed and Beswick released the clutch, the car would squat hard on its rear suspension, the front end rising dramatically as 650 horsepower tried to rotate the entire chassis around the rear axle. The rear tires, wrinkle wall slicks designed to flex and absorb the initial shock of the launch, would deform visibly as they clawed for traction. First gear would be consumed in approximately 1.2 seconds. The shift to second came at 7,500 RPM, a violent bang that tested every component in the drivetrain. Third gear arrived almost as quickly, and by the time the car crossed the quarter-mile finish line, it was traveling at over 134 miles per hour. The sound inside the car was indescribable. Modern cars have sound deadening and insulation and electronic noise cancellation. Beswick's GTO had none of that. The tunnel ramp scream came through the firewall unfiltered. The exhaust, running through open headers with no mufflers, was a physical force that you felt in your chest more than hurt with your ears. The combined effect was sensory overload, a wall of noise and vibration and acceleration that lasted roughly 10 seconds and left you momentarily disoriented when it was over. Pontiac's reaction to all of this was fascinating and, frankly, a little sad. Officially, they continued to maintain that tunnel rams were unnecessary for their engines. Their marketing department never acknowledged Beswick's achievements in any official capacity. Their engineering department never released a factory tunnel ram option or even a dealer-installed performance kit. But behind closed doors, things were different. Internal memos from Pontiac engineering, some of which have been obtained by automotive historians, show that several engineers were acutely aware of what Beswick was accomplishing. At least 2 formal proposals were submitted to develop a factory-sanctioned tunnel ram package for the 455. Both were rejected by management. The reasons for those rejections tell you everything you need to know about the forces that were killing the muscle car era. By 1971, General Motors was under enormous pressure from insurance companies, government regulators, and safety advocates. The days of advertising horsepower figures and quarter-mile times were ending. Pontiac was already dealing with corporate mandates to reduce compression ratios and detune engines for emissions compliance. Releasing a factory tunnel ram, an unapologetically race-oriented component, would have been a public relations disaster at a time when the company was trying to project a more responsible image. The bean counters also killed it on pure economics. A tunnel ram package would appeal to maybe a few hundred racers nationwide. The development cost, warranty liability, and regulatory headaches simply couldn't be justified against such a tiny potential market. And so, Pontiac's 455, one of the finest big block architectures ever created, went to its grave with its full potential unexplored by the company that built it. But Beswick's influence extended far beyond the Pontiac community. His success with the Tunnel Ram 455 inspired experimentation across the entire big block spectrum. Within a year of his dominance becoming common knowledge, tunnel rams were appearing on Ford 460s, Buick 455s, Oldsmobile 455s, and even some of the more exotic combinations that creative racers were assembling. The fundamental lesson Beswick taught was universal. Don't accept the manufacturer's opinion about what your engine can do. Test it yourself. Challenge the assumptions. The factory engineers are brilliant, but they're also constrained by budgets, regulations, timelines, and committee decisions that have nothing to do with maximum performance. This is where it gets really interesting from a historical perspective. The aftermarket industry responded to Beswick's success with remarkable speed. Companies that had previously focused their Pontiac product lines on basic bolt-on components suddenly began developing serious race-oriented hardware. Tunnel ram manifolds specifically designed for Pontiac port geometry appeared from multiple manufacturers. Camshaft grinders developed new profiles optimized for tunnel ram applications, with duration and lift specifications that would have been considered insane just a few years ago. Carburetor companies started offering tunnel ram calibration kits with pre-selected jets, power valves, and accelerator pump components that took some of the guesswork out of the tuning process. None of this would have happened without Beswick proving the concept worked. The economic ripple effects were significant on a personal level too. Beswick's speed shop in Roswell saw its business roughly triple in the 2 years following his tunnel ram breakthrough. Racers from across the Southeast and eventually from across the entire country would trailer their cars to Georgia to have the farmer work his particular brand of magic. A full Beswick tunnel ram build wasn't cheap. The tunnel ram manifold itself cost approximately $400 in 1971 money. Each Holley carburetor added another $200. The custom camshaft was $300. Forged pistons, rods, and machine work added another $1,500. Cylinder head porting ran $600. By the time everything was assembled, tuned, and ready for competition, a customer was looking at roughly $3,000 in modifications, which translates to approximately $22,000 in today's money, for a naturally aspirated engine. But serious racers paid it gladly because the results spoke for themselves. Prize money at major NHRA events could reach $5,000 for a class win, and contingency sponsorships added substantially to that. A competitive season could gross $30,000 or more, making the investment in a Beswick-built engine a sound business decision. Modern technology has validated virtually everything Beswick discovered through trial and error. Contemporary Pontiac builders, using computerized flow bench data, engine simulation software, and precision CNC machining, have pushed naturally aspirated 455 combinations past 700 horsepower using evolved versions of his tunnel ram formula. Electronic fuel injection has replaced the temperamental Holleys, eliminating the constant jetting changes that weather variations demanded. Roller camshafts have superseded flat tappet grinds, allowing more aggressive valve acceleration profiles without the lobe wear concerns that limited Beswick's cam choices. But the fundamental principle, using intake runner length to create resonance tuning that rams extra charge into the cylinders, remains exactly the same. The physics haven't changed, only the tools for exploiting them have improved. And here's something that really puts Beswick's achievement in perspective. He did all of this without any of the technology we take for granted today. There were no computer simulations to model airflow, no wide-band oxygen sensors to provide real-time air-fuel ratio data, no data acquisition systems to record every parameter of a run, no internet forums to share information and troubleshoot problems. Beswick had a dyno, a set of spark plug reading glasses, decades of accumulated experience, and an intuition for engine behavior that bordered on supernatural. He would make a change, run the engine, read the plugs, interpret the results, and make another change. It was empirical engineering in its purest form. And the fact that his results have been validated by modern technology only underscores how deeply he understood the fundamental principles at work. The story raises a question that I think about a lot. What would have happened if Pontiac had embraced tunnel ram technology instead of dismissing it? What if they had channeled even a fraction of their engineering resources into developing a factory race package built around the tunnel ram 455? Could they have dominated NHRA competition the way Chrysler did with their Hemi program? The potential was clearly there. Beswick proved that with a fraction of the resources available to a major manufacturer. A factory-backed tunnel ram program with proper R&D support could have produced something truly extraordinary. But the opportunity passed. The muscle car era ended, emissions regulations tightened, insurance rates climbed. Pontiac moved on to catalytic converters and unleaded fuel, and the 455 faded into history as one of the great what-ifs of American automotive performance. Today, original Beswick-built tunnel ram engines are among the most coveted artifacts in Pontiac collecting circles. A documented engine with verifiable provenance can add $50,000 or more to a car's value. The tunnel ram manifolds themselves, particularly the early Edelbrock and Wyan castings that Beswick favored, command $3,000 or more when they surface at swap meets or in estate sales. These aren't just engine parts, they're pieces of American racing history, tangible evidence of what one individual can accomplish when they refuse to accept the limitations that others impose. In the end, Arlen Besswick's tunnel ram 455 represents something that goes beyond horsepower numbers and quarter-mile time slips. It represents the fundamental spirit of American hot rodding, the belief that factory engineers don't have a monopoly on good ideas, that innovation can come from anywhere, that the guy in the farm workshop might see possibilities that the corporate design studio overlooks. Pontiac said the 455 didn't need a tunnel ram. Beswick proved them wrong. Not with theoretical arguments or academic papers, but with elapsed times and trap speeds that were impossible to dispute. He didn't just outsmart Pontiac's engineering department. He revealed potential that their own engine possessed, potential they either couldn't see or chose not to pursue. And when you think about it, that's what makes stories like this endure. In a world increasingly dominated by computer-designed, committee-approved, focus group-tested engineering, there's something profoundly satisfying about a Georgia farmer who looked at the biggest automaker's most powerful engine and said, "I can make it better," and then did exactly that. 1/4 mile at a time, one spark plug reading at a time, one late night in the shop at a time, until the evidence was undeniable and the record books told a story that Pontiac's engineering memos never would. So, the next time someone tells you that something can't be done, that the experts have already optimized everything there is to optimize, that there's no room left for improvement, remember Arlen Besswick and his tunnel ram 455. Remember that a farmer with curiosity and determination proved an entire engineering department wrong. And remember that sometimes the most extraordinary breakthroughs don't come from where you'd expect. They come from the people who refuse to stop asking, what if? What's the most impressive engine build you've ever encountered? Was it a factory masterpiece engineered by teams of PhDs? Or was it a privateer's creation, assembled in a home garage that defied every expectation? Drop a comment below and share your story. And if you enjoyed this deep dive into one of drag racing's most legendary David versus Goliath tales, make sure to subscribe and hit the notification bell. We're just getting started exploring the incredible stories of individuals who refused to accept limits and changed motorsports forever. Until next time, keep those engines screaming, and remember, sometimes the best engineering comes from the most unexpected places.